Okay guys, so we're practicing with Lewis dot structure, shapes, and polarity. I've got a set of examples we're going to work through. So we're going to take each one all the way across and then restart. So my first example I have is carbon dioxide. In order to do any of this, you have to be able to draw the Lewis dot structure. If you're not good at that, go back to the previous videos and practice, but you have to have the correct Lewis dot structure for each molecule before you can work ahead. So CO2, you should know how to draw. Carbon needs 4 bonds. Each oxygen needs 2 bonds, so I end up having a structure that looks like that. The carbon has a double bond to both oxygens. So at that point, I can look at it and say, okay, what's the steric number of my center atom? So I focus on carbon. How many different things are coming off the carbon? A double bond only counts as one group. So I've got a double bond to one oxygen, a double bond to the other oxygen. So that's 2 groups. So the steric number is 2. Electron geometry. Well, the steric number and electron geometry are connected to each other. If it's 2 groups, the only geometry that we know for 2 groups is linear. Okay, so the CO2 molecule, the electron geometry is going to be linear. Next step, molecular geometry or the shape. So this is where I say, okay, take the electron geometry, look at the structure, and I'm going to take off the lone pairs. Specifically, though, I'm looking at the center atom. So if I take off the lone pairs, carbon doesn't have any. If carbon doesn't have any lone pairs, then that means that molecular geometry and electron geometry will be the same. So it's going to be linear. So that brings me to the bond type. If I look at CO2, pick one bond, the bond between these 2 atoms, is that bond polar or nonpolar? You should know that oxygen is more electronegative than carbon based on the trend that we learned. So I could draw an arrow and say, okay, that bond, the electrons are being pulled towards oxygen. There is a significant pull there, so that's a polar bond. Under bond type, and basically I'm looking, if I have any polar bonds in the molecule, then I'm going to put under bond type polar. I do have polar bonds. Because if I don't have any polar bonds, I can't have a polar molecule. Okay, and that's what this is all about, is trying to find out, is this molecule polar or not? So, I have polar bonds, but there's 2 of them. One of them pulling that way, the other one pulling that way. And I have decided this is a linear molecule. Along the way, I decided it was linear, so I know that these 2 oxygens should be on opposite sides. And if one's pulling me this way, and the other one's pulling me this way, and they're evenly spaced out, they will cancel. So even though I have polar bonds, the molecule is going to be nonpolar. So it's a nonpolar molecule. Now, the tricky thing with this, though, is that in the very beginning of the problem, I might not always say, hey, fill out the whole table. I might just ask you in the beginning, hey, is CO2 a polar molecule or a nonpolar molecule? The only way to figure that out is by going through this whole process. So even though asking, is CO2 polar, sounds like a yes or no answer, there's a lot of work that has to go into it to figure out the proper answer and be able to support it. CO2 is polar because it's a linear molecule with polar bonds. The polar bonds are pulling against each other, which makes them cancel out. Therefore, I end up with a nonpolar molecule. You have to go through that whole process to be able to get the final answer over here. Okay? So, next molecule, CHCl3. So I've got a carbon, I've got 1 hydrogen, and 3 chlorines. And of course, all my chlorines should have 3 lone pairs. On the test, if you leave off lone pairs, you will get counted off. So that's my Lewis dot structure. How many groups are there around the carbon? And there are clearly 4 different things there. Remember, a lone pair on carbon would count, but the lone pairs on chlorine are irrelevant. We're focused on the center atom. The center atom only has 4 things on it. So the steric number of CH3Cl, or CHCl3, is 4. Electron geometry, if it's 4, 4 is always tetrahedral. That's just a connection you have to make. The steric number always matches up with a specific electron geometry. They are a pair. You can't switch them back and forth with others. Okay? Now, molecular geometry. I look at the molecule, I say take off all the lone pairs. Does carbon change? The answer is no. So the electron geometry, the molecular geometry are going to be the same. So now I'm finally ready to look at polar bonds. Do I have any polar bonds here? And we've said before, the CH bond's a little bit polar, but the CCl bond is going to be significantly polar. So each bond from C to Cl, chlorine is more electronegative. So I could draw, you don't have to draw this out every time, I could draw the arrow showing the electrons being pulled out towards the chlorine. I could do that on each of those bonds. Okay? So the answer is, do I have any polar bonds? Yes, I do. So under bond type, I put polar bonds are present. So I'm just going to put polar bonds, yes. Check. Okay? So I have polar bonds. That creates the possibility that the molecule might be polar. But then I have to look back and say, okay, I've got 4 bonds. They're spread out tetrahedrally. Are they going to cancel out? So I think, is this molecule symmetrical? Are the polar bonds evenly distributed all the way around? And the answer is on this one, not quite, because the 4 groups around carbon, they're not all the same. If I think I'll be pulled 5 steps this way, 5 steps that way, 5 steps that way, but I only take 2 steps this way, the hydrogen, the amount that it pulls the electrons is not even with all the others. That's going to create an imbalance. And if it's not balanced, that means it's not symmetrical. If it's not symmetrical, then that means the bonds don't cancel each other out, so it is a polar molecule. So CH-Cl3 is a polar molecule. Okay, so that one's done. Next one, CH2Cl2. All right, now, this one, a little tricky because the way you draw it can have a lot of influence on your answers. If you draw this molecule, say, well, the chlorines probably want to be on opposite sides, which for some reason a lot of people do that. If you draw it like that, when we get to the end and we ask if things cancel out, it kind of looks like the 2 chlorines are pulling against each other and the 2 hydrogens are pulling against each other. It kind of looks like that might cancel. But if I go back to my model, even though if I draw my chlorines on opposite sides, so I can build a model and say, okay, the green atoms are chlorines, the white atoms are hydrogens, it looks like they're opposite sides, but really when I twist it, I can say, both chlorines are on the same side and the hydrogens are on the same side. It's all about, since it's tetrahedral, this drawing is not really accurate. A 2-dimensional drawing of a 3-dimensional molecule is never going to represent it properly. So this is what the molecule looks like, and it doesn't matter if you put the 2 hydrogens on the same side of the molecule or twist it, put one on top and one on bottom. It's the same either way. No matter if I switch any of these atoms, it's always going to give me the same product, okay? So, when I look at this, what's the steric number around carbon? The answer is 4. There's 4 things around carbon. Electron geometry, 4 is always tetrahedral. There's no lone pairs on carbon, so the molecular geometry is also going to be tetrahedral. I asked myself, do I have any polar bonds? Yes, the CCl bond is polar. And then I asked myself, are the 4 bonds symmetrically arranged? Again, this is where I said it kind of looks, because I drew it this way, it looks like everything's opposite and going to cancel, but the real molecule is not. The 2 chlorines on one side, 2 hydrogens on the other side, this is not symmetrical. The poles don't cancel each other out. The chlorines are stronger, than the hydrogens are. So this molecule has polar bonds. It's not symmetrical, so the molecule stays polar. Okay, and that's the end of that one. We got two more that we'll do quickly. If you draw out SF4, you should get something that looks like that. All my fluorines should have their lone pairs on them. So that's my molecule. Now, I drew it realistically the way it's supposed to be drawn, where as you draw it, you have your 4 fluorines in your lone pair. If you don't know where to put them, it's okay. I'm not really overly worried about whether your drawing is perfectly arranged. It's more about getting the right bonds in the right lone pairs and on the right atoms. Okay? But if I have that structure, the steric number, how many things are on sulfur? Well, there's 4 fluorines and 1 lone pair, so the steric number of this one is 5. Electron geometry, if I have 5 groups, you have to memorize the basic structure for 5 groups. Is trigonal bipyramidal. I'm going to abbreviate trig bipyramid, but it's trigonal bipyramidal. The molecular geometry, this is where I say, okay, on sulfur, there is a lone pair right there. It does occupy a position on my trigonal bipyramidal. But if I cover it up or erase it, it gives me a different shape, and this is, again, it's one of the ones you have to memorize. So if you look up 5 groups with 1 lone pair, the name is seesaw. Well, basically, if I turn my head sideways, pretend that this is the base of the seesaw, that's the center, and this is the board that 2 kids would sit on and go back and forth. It actually resembles a seesaw if you look at it from the right angle. So the names are not just made up, they're supposed to remind you of what the shape looks like. So this one, the molecular geometry of 5 groups with 1 lone pair is seesaw. Do I have any polar bonds? Fluorine's more electronegative than anybody else. Anybody he shares electrons with, he's going to pull them towards his side. So yes, I have polar bonds. And then, are they symmetrically arranged? Well, again, if there's 5 groups, if all 5 were the same, that would be symmetrical. But since one group is a lone pair, that throws off the symmetry, pushes all the fluorines to one side. So it's not symmetrical, that means it's polar. SF4 is a polar molecule. All right, last one. PCl5. I've got 5 chlorines. Now, I know phosphorus has 5 valence electrons. If I make 1 bond to each chlorine, that's going to use up all 5 of phosphorus's valence electrons. So I know that phosphorus is not going to have a lone pair. The chlorines, I'm going to be lazy. All of them ought to have 3 lone pairs on them. Okay, but really for this discussion, if they weren't there, you could still answer all the questions. But I do want, anytime you draw a Lewis dot structure, like on the test, I want to see all the lone pairs. So you got to show everything. Okay, but PCl5, the steric number on phosphorus is 5. The electron geometry is trigonal bipyramidal. When I look at this molecule, the molecular geometry, take off the lone pairs. Phosphorus doesn't have one, so the molecular geometry is going to be the same, trigonal bipyramidal. Then I go to the bond type. Do I have any polar bonds? And the answer is yes. Chlorine is more electronegative than phosphorus, so it is going to pull out. So that is going to be a polar bond. So bond type, polar. And under molecule type, I look for symmetry. There are 5 groups. They're all the same. So this is symmetrical. The polar bonds cancel each other out. The molecule will be nonpolar. So that's it. Did a lot of examples. Hope that helps everybody.